Hi, everybody. In this video, we're going to look at more about polynomial functions and their zeros. So let's keep going with that idea. So we have the rational zero theorem, which says that if f of x is the following function, so that's just our general form for a polynomial. So you have some coefficients and x's raised to powers all being added together. If it has integer coefficients, and if p over q is a rational number written in lowest terms, and if p over q is a zero of f, then p is a factor of the constant term and q is a factor of the leading coefficient. So this definition is, I think, really complicated for what it is. It's really not as bad as it sounds. So basically what it's telling us is how to find possible zeros or solutions to polynomial equations. And what we do is that the values that we can test happen to be the ratio of factors of the constant term to factors of the leading coefficient. So let's actually do an example there, and I think it'll make a little bit more sense. So remember, for a rational zero, what you're looking for is that when you plug in that number, the output is zero. If it's real, it's also an x-intercept. So you would see that as well. Or if it's rational, right, that's real. So you would see that that's x-intercepts as well. So this is not going to give us the exact answers. It's going to give us possible answers. So your rational zeros have to come from this group of possible values. So what you do is you first look at the factors of your constant term. Now our constant term here is 4. So if you think about 4, well, 1 times 4 is 4, and also 2 times 2. So there's 3 main factors here, but they also could be plus or minus, because you could do -1 times -4 or -2 times -2. So when you're talking about factors, we do include negatives as well. And then you look at the factors of your leading coefficient. So our leading coefficient here it would be the x fourth term. There's a 1 there, so it's -1. And my only possible factors of -1 are 1 times -1. So plus or minus 1. And then what you do is you put these together as a ratio. So your possible rationals, or rational zeros, I should say, are, and what you do is you look at the factors of your constant term divided by the factors of your leading coefficient, in that order. So the constant term always goes on top. So for instance, for my constant term, I have 1, 2, and 4. So I'm going to take each of those and divide it by 1. So I have 1 over 1 is 1. I have 2 over 1 is 2, and I have 4 over 1 is 4. Now, you're also going to add in plus or minuses everywhere, because they could be negative or positive. So your possible rationals are plus or minus 1, plus or minus 2, plus or minus 4. So what I'm doing here is I'm not finding the exact answers, unfortunately. I'm only finding the possible ones that could be answers here, or that could be the zeros. So I have 6 to try, and we'll do some examples later on with this, but at this point you could do like a trial and error process to see which ones actually do work, and such that when you plug them in, you get 0 as your output. But at least it narrows it down for us. We don't have to try every single example. Now what you could do is you could also graph this. So I'm just going to show you the graph from your book. See if I can kind of bring it over here. All right, so this is the example that we're looking at. And if you graph it, you get a graph like this. So you can see that it crosses the x-axis at -2 and +2. So these are your actual rational zeros. Remember that your real zeros, like real number zeros, are also x-intercepts. So you can see them on the graph. So, you know, plus or minus 4, plus or minus 1 are not going to end up working, but the plus or minus 2 end up working here, and these are going to be your rational zeros. All right, let's do another example. So we're going to list all possible rational zeros for this next polynomial. So remember, you're looking at the constant term So my constant term here is -2. So 1 times 2 is 2. That's about all you're going to have here. So your options are +or -1 and +or -2. And then you're going to look at your factors of the leading term, or leading coefficient, I should say. Leading term has the x cubed in this case, so the coefficient is 15. Now there's lots of options here, right? 15 is 1 times 15. You could also do 3 times 5, and all of these are going to be plus or minus. And then now you look at the ratio. Just remember that when we set up the ratio, it's always the constant values on top and the leading coefficient values on bottom. So what we're going to get here for our ratio is you'd have 1 over 1, 1 over 3, 1 over 5, 1 over 15. And then of course, plus or minus for all of these. And then you'd also do the 2. So 2 over 1, 2 over 3, 2 over 5, and 2 over 15, and plus or minus for all of these. Now, if you can simplify, you do want to do that. So our possible zeros, and again, possible rational zeros, I should say, are plus or minus 1, plus or minus 1/3, plus or minus 1/5. Sorry, that doesn't look good. 5, 1/5, plus or minus 1/15, plus or minus 2, plus or minus 2/3, plus or minus 2/5, and plus or minus 2/15. So we have 1, 2, 3, 4, 8. So we have 16 options here to try, which is definitely kind of a lot, right? But at least it's not infinite. So I guess you could technically try infinitely many, right? Just to keep plugging things in to see if you can get a 0. So remember, when we have zeros, you would get a 0 as your output when you plug in one of these values. And again, what you could do is you could try graphing to see if you can maybe narrow down the region and look for those x-intercepts. And I'll tell you here, again, we haven't done it yet, but there's actually 3 of them that work, and -1, -1/3, and 2/5 all work. Now I'm giving you the answer there, but how would you know? So what you could do is, one, you could graph and you could look for those x-intercepts. So try to narrow down that way to see if you can actually find the x-intercepts. Now some of these are a little bit hard because 1/3, 1/5, they're kind of close together on the graph, so you may have to be a little bit more careful there. But you could try your graphing first and look for those x-intercepts. The other thing you could do is you can do trial and error. So you could take all these values and you could plug them into the function and see which ones give you that 0 when you plug it in. So for instance, if you plug in -1, you're going to get 0 as your answer, so you know it works. Whereas if you plug in 2, you're not going to get 0 and you know it doesn't work. Another way you could do it is to test all these with synthetic division. So when our remainder is 0, that is a 0 of the polynomial. So you could try synthetic division on all of them and see which ones have remainder of 0. So there's different ways that you can test this, but none are super easy. I would say graphing is probably your easiest bet here, if you could see it visually. All right, so let's take it that next step now. So notice the question has slightly changed. Instead of finding all possible zeros, we're asked to actually find all zeros. So we don't just want the possible answers, we actually want to take it to that next step here and find the actual answers. So I'm going to start by finding my possible ones first. So I'm going to look at my factors of my constant term, and then I'm going to divide those by the possible factors of my leading coefficient. Now my constant term here is -6. My leading coefficient is just 1, which makes it nice. So for 6, my possible options are ±1 and ±6, or ±2 and ±3, right? 2 times 3 is 6, 1 times 6 is 6. Now for 1, this is nice. My only option here is 1. So we're going to do all of those divisions out. So I have 1 divided by 1 is 1, 2 divided by 1 is 2, 3 divided by 1 is 3, and 6 divided by 1 is 6. And again, just keep in mind that you do have all the plus or minuses because you could have negatives in there as well. So I have 8 possible options here for zeros to try. Now, like I've said before, there's different ways to think about this, right? So one way is to graph and see if you can find any x-intercepts. Another way is to plug in to find the values that give you 0 as an output. And the third way is to use synthetic division since a remainder of 0 associates with a factor. Okay, so there's sort of three main ways that you can do this. Now, I want to actually look at the graph of this first. So let me bring up my Desmos. And we're going to share my new screen. I apologize, my video is not on today. For some reason, I can't get my camera to load with Zoom, but that's okay. We'll keep going. So let's see, f of x equals x cubed plus 2x squared minus 5x minus 6. Okay, so if I look here, it looks like I have 3 zeros, or 3 rational zeros, I should say. So I have it at -3, I have it at -1, and I have one at 2. Now, notice that my highest power is a 3 here, so I can have up to 3 solutions. So this must be all of them, right? I actually have up to 3 real solutions, I should say. So if I have 3 real solutions here, I must have them all. So graphing is a really nice way because I can tell you right away that my zeros are going to be 2, -1, and -3. But let's say that you're not graphing, or let's say that you have to find it a different way. So another way to do it, and this is fine if you just don't mind testing, or if you don't have too many options to test, is what you could do is try the different values. So for instance, if I plug in f of 1 to my formula here, I get 1 cubed plus 2 times 1 squared minus 5 times 1 minus 6. So I have 1 plus, let's see, 1 squared is 1 times 2 is 2, minus 5 minus 6. Now you can clearly see that this is not going to be 0, right? I have 3, let's see, minus 11. So I'm at -8. So this does not work. If I plug in f of -1, which we saw from the graph should be a rational 0, I have -1 cubed plus 2 times -1 squared minus 5 times -1 minus 6. Let's see, -1 cubed is -1. -1 squared is 1 times 2 is 2. Here I would have +5 minus 6. So I'm actually getting +7 minus 7, which is 0. So that's one of our zeros, right? And you could test the other values that way too. So that's another strategy you could use. The third strategy is kind of nice because it doesn't require you testing every single value. You just have to keep testing until you find the first value or maybe the second value too, and then usually we can factor the rest. So let me show you how to do that. Okay, so I'm going to show you one that we know works just so you can see the process here. So I'm going to test -1. And I'm going to do synthetic division here. So on my inside, I have a 1, a 2, a -5, and a -6. And when you're doing synthetic division, you're looking for a remainder of 0. Let's see, -1 times 1 is -1. I add these together. -1 times 1 is -1. Add these together. -1 times -6 is +6. I add these together. And that's what you're looking for. You want to have a remainder of 0. So when you have a remainder of 0, then you know that this is actually a factor. And in this case, my c is -1. So x minus -1 would be x plus 1. So this is one factor of that polynomial. And another factor is going to be right here. So I started with cube, which means I'm going to square. So it's going to be x squared plus x minus 6. So what I have now is that my original polynomial right here can actually factor into x plus 1 times x squared plus x minus 6. And again, we're trying to find the 0, so we're setting this equal to 0 to solve. Now, hopefully, if you find that first 0, then and you use synthetic division, then you can just kind of factor the rest. That's the goal. And it should factor this way for the remaining quadratic here. And then what we do is we set each piece equal to 0 and we solve that way. So I have x equals -1, x equals 2, and x equals -3. So you can see that you have the same 3 zeros that we did when we were looking at the graph. So 3 different strategies that you can use to actually find the zeros. Obviously, I think the graphing is usually the easiest, particularly if your numbers are integers, right? If you start getting into messy fractions, then it may be hard to tell exactly on the graph which fraction is which. The second choice is probably going to be your synthetic division, only because once you find 1 0, hopefully you can factor the rest on your own and not have to keep testing all the other ones. So that tends to be what is usually recommended as a strategy there. All right, let's try another example here. Okay, so same question, find all zeros. And I'm going to start with my possible zeros first. All right, so I'm looking at the factors for the constant term over the factors of my leading coefficient. So my constant term here is -3, and my leading coefficient happens to be 1 again, which is nice. So for -3, it's really just 1 and 3, and of course, plus or minus. And then for 1, it's just 1. So I'm going to divide each of these. 1 divided by 1 is 1, 3 divided by 1 is 3. So here it's kind of nice. I only have 4 possible values. So let's go ahead and start testing these and see if we can find one. All right, so let's try and test. We'll test 3 first. So I'm going to use synthetic division here. I do recommend at home though you try graphing. So try graphing this and see if you can find any possible rational zeros to start. It's very helpful. Maybe we'll check it at the end. So let's try testing 3. So I use my 3, and this gives me a 1, a 7, 11, and a -3. I bring down the 1. 1 times 3 is 3. Add to get 10. 3 times 10 is 30. Add to get 41. All right, now here I'm at what? 123. This is definitely not 0. So this one does not work. So let's test -3. -3 times 1 is -3. I add and get 4. -3 times 4 is -12. I add to get -1. And here I would get +3, which is 0. So because my remainder is 0, this one must work. Remember, this is your C value. So x minus C is a factor. So x minus here -3 would be x plus 3 for your factorization. Now your other factor comes from here. So if we were starting with a cube, this is going to be a square. So one of my factors is x plus 3, and then I have x squared plus 4x minus 1. And then remember, I'm looking for the zeros. So I'm setting the whole thing equal to 0 to solve. If you're not looking for zeros, you wouldn't set it equal to 0. Now, ideally, you would try to factor this, but if you try factoring it, you're going to see that it actually doesn't factor. So what do you do when it doesn't factor? You can still keep going. So we do have that x plus 3 equals 0. So we know that x equals -3 is one solution. And then I can still set this equal to 0. And even though it doesn't factor, I could use my quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And remember, you're just using it for this part right here. So my b is going to be 4, my a is 1, and my c is negative 1 here. So I'm going to have negative 4 plus or minus the square root of 4 squared minus 4 times 1 times negative 1 all over 2 times 1. So I have 16 and then plus 4. That would give me 20. Now you can factor root 20. That would be root 4 times root 5. So it does simplify as 2 root 5. And remember that 2 can be put over both parts, so that's a little bit easier. So we get that x equals negative 2 plus or minus root 5. So there are my 3 zeros. Are negative 3, negative 2 plus root 5, and negative 2 minus root 5. Now, a couple of things here before we finish this problem. So notice that one, they are all real numbers. Negative 2 root 5 and negative 2 minus root 5, excuse me, that's a real number. It's not imaginary. The root 5 is positive, right? It's not negative. So these are real numbers. They're just decimals. So you could find them on your calculator here if you wanted to. So let's bring up my calculator. Right, so if I wanted to just find the first one, I could do negative 2 plus the square root of 5, and I have the value of about 0.236. So that is a real number. Now, if you're wondering why these values weren't here in our possible answers, it's because your possible zeros only give you the rational ones. It doesn't tell you about any imaginary ones, and it doesn't tell you about any that are irrational, like negative 2 plus root 5 and negative 2 minus root 5. Those are not rational because those decimals keep going on and on forever, and they don't repeat. So when you're using this theorem, it's important to remember that you're only checking the possible rational zeros, but there could be other zeros there as well. There could be irrational ones, or there could even be imaginary ones. So that's kind of one thing to keep in mind with this, not formula, but this theorem, I guess, is that, you know, when you're checking, you're not checking every possibility, you're just checking all the rational possibilities, but there could be imaginary or irrational answers as well. So the synthetic method is kind of nice because, you know, if you were up here and just testing by plugging in, you're going to miss the other answers, right? Now, if all of these work and you have all your zeros, right? Let's say you've checked with your graph, then that's okay. But here, you know, if we checked all of these and we didn't check anything else, we would miss our 2 irrationals. So that's why it is recommended to do the synthetic division instead of just testing kind of individually. It tends to be faster, but then it also accounts for those cases where maybe not all the answers are rational. So some problems do not have answers that are rational.